Hi, today we're going to explore where irreversibility comes from at a microscopic level and how to quantify it. Remember, Newton's equations are reversible in time. The elastic collision between two marbles satisfies Newton's laws whether you're playing a movie forward or backward. However, if I take an example of 3 balls on a pool table and play it backwards, well, let's look at it forwards first. That's quite usual. Anyone who plays pool has done it. But playing it backwards, it looks a lot less likely. The backwards collision would still satisfy Newton's laws, conservation of momentum and energy, but you'll agree that getting those 2 balls to hit the last one just right to give all of the momentum to the third ball so that they both stop in place, that process would have taken a great deal of effort to get right. It is quite unlikely. If I take a large number of balls and do the same experiments, like here, with 1 ball hitting 9 others, ending up with a lot of balls bouncing around quite randomly, you'll agree that the backwards process, where all the balls converge to give all the momentum and kinetic energy to that one single ball so that all remaining balls stop in place in a nice pattern, well, that's just not going to happen. Even though mechanically, again, it is possible. Statistically, it's just very, very unlikely. So that's an example of how disordered systems just don't tend to go to more ordered systems. From these examples, we see irreversibility appears naturally with increasing numbers of balls. The direction of time is a statistical effect. To understand this in more detail, let's look at the free expansion of a gas again. We look at a gas or a set of balls in this double chamber with 9 molecules starting all in the left chamber with some random velocities at the beginning. We let them run and collide elastically. At the same time, we'll count how many balls are in the left chamber and how many in the right chamber, and we'll plot a histogram of how often a certain number of balls is in the left. So initially, we have n left, the number of balls in the left, equal to 9, and so we have 1 bar in the histogram. We now run the simulation. Incidentally, I'll put the MATLAB script for this online if you want to play around with it. As you see, some balls enter the right chamber, bounce in and out. Sometimes the number of balls in the left is 4, sometimes it's 5, sometimes it's 6, and sometimes it's even 1. While this is running, we'll introduce the notion of microstate and macrostate. A macrostate, or microscopic state, is a set of positions and velocities of each individual molecule. Every detail counts here. Every time we have a molecule at a different position or velocity, we have a new microstate. If we have multi-atomic molecules, even the internal state of the molecules will matter for the microstate. So in this simulation, each frame of this animation represents its own microstate. In contrast, a macrostate or microscopic state is characterized by the macroscopic properties. For example, for a gas, that would be the set of pressure, temperature, and volume. In our example, with only 9 balls, it's a free expansion, so the temperature or average velocity here isn't changing. Neither is the volume. If the temperature and volume are constant, then the pressure is directly proportional to the number of molecules. So the number of molecules in the right or left chamber are representative of the pressure in the right or left chamber. Just looking at the position of the balls, the macroscopic state in the left chamber is here thus entirely characterized by n left, and the macrostate in the right chamber by the number of balls in the right, which is just the remaining balls. A same macroscopic state, say n left is equal to 4, can be realized by many, many different microscopic states. Same in a gas. The same pressure, temperature, and volume can be achieved by many, 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 many different combinations of actual positions and velocities of individual molecules. Going back to our animation, we see that the macrostate, represented by n left, or the pressure in the left chamber, doesn't change quite as often as the microstates. And as we see from our histogram, it tends to take some values much more often than others. The number of balls on the left is more often than not 4 or 5. So more often than not, we have 4 or 5 balls in the left and in the right. And even though nothing forbids all balls to be on one side, it's very rare that it happens. That means having roughly the same amount of balls in each chamber, or in terms of pressure having the same pressure in both chambers, is what we observe the most often. So what we've seen here is that the pressure equalizes between the 2 chambers. Why is that, and how does it generalize to larger number of molecules? To gain further understanding, let's disregard the exact positions and velocities of the molecules for now, and assume microstates are just characterized by whether a given ball is in the left or in the right chamber. Let's look at a small example, and specifically how many different ways of putting 4 balls in 2 chambers there are. We'll take them to be colored black, green, red, and blue to be able to distinguish them. To have all 4 balls in the left, there's only one way. All balls have to be there. To have 3 balls on the left, so that's the macrostate where 3 balls are on the left and 1 on the right, you can have either the blue, the red, the green, or the black ball that are in the right chamber. So there are 4 different possibilities, or 4 different microstates for that one macrostate. To get 2 balls in each chamber, there are 6 ways. To get only 1 ball in the left chamber, well, that means we have to put 3 balls in the right chamber, so those last 2 cases are actually just a symmetric of the first 2. So if all microstates are equally likely because the balls bounce randomly around, the macrostates are not equally likely. We get the probability of a macrostate by dividing the number of microstates that make it up by the total number of microstates that are possible. Adding them up, there's a total of 16 microstates possible, of which 6 correspond to n left equals 2. So the probability of having 2 balls in the right and left chamber is 6 divided by 16, which is higher than for the other 4 cases. If we look at it in terms of order or disorder, having all balls in one chamber is more ordered. We know exactly where all the balls are. Whereas for the macrostates, where there are 2 balls on the right and 2 on the left, we don't know which ball is where. That could be anywhere. So that is the most disordered state. So in this case, we see the most disordered macrostate is the one which has the most possible microstates, and it is also the one that is the most likely to be seen. More generally, for a total number of n balls, you can calculate how many microstates there are for a number n left of balls to be in the left chamber using the binomial coefficients, if you've seen these in math. You just need to pick n left balls among n. These are the balls that will go in the left chamber. So the number of microstates corresponding to the macrostate characterized by n left is a binomial coefficient of n over n left. For 3 balls out of 4, that gives us indeed 4. How many microstates are there in this example? How many total number of microstates? Well, for each ball, it can be either in the left or in the right chamber. So there's 2 possibilities for the first ball. There's 2 possibilities for the second ball too, so that's 2 times 2 possibilities. For the next, there's 2 possibilities again, so that's 2 times 2 times 2 ways of distributing 3 balls between the 2 chambers, or 8 total microstates, etc. So if we only care about in which chamber the balls are, for n balls, there's 2 to the power of n microstates. The probability of a macrostate then becomes the number of microstates corresponding to the macrostate, so the binomial coefficient of n over n left, divided by 2 to the n. If we take more balls, or more molecules, the statistics change as well. Here we have the probabilities calculated using the binomial coefficients of each macrostate for 9 balls, the same number we use in our simulation. That's here on the left and on the top left. And the statistics also for 20 balls, 200 balls, and 1,000 balls. These probability bell-type curves, calculated with our formula from the previous slide, are called binomial distributions. You see that the more balls there are, the narrower the distribution becomes. Pausing on the plot in the bottom right here, for n equals 1000, the probability of having less than 400 balls in the left or right chamber is already 10 to the minus 10. That is, if you watched a similar simulation as we did for 9 balls but with 1000 balls, you'd see this happen once every 300 years or so. Again, for a total of 1000 balls, the probability of having less than 350 balls in any one chamber is so low, you'd have to watch the simulation for the duration corresponding to about 100 times the age of the universe before you get to see it once. So for large numbers of molecules, it becomes very, very unlikely to have much of a dissymmetry between the 2 chambers. And again, we see the most disordered microstates, the one which can be realized by the largest number of microstates, are the most likely we will actually observe. Remember, 1000 molecules is nothing compared to the Avogadro constant. For the Avogadro constant, for n equals na, we are left but with a peak in the middle with no width at all. So for a gas, or an actual gas, say a mole of gas, we know with a very, very high relative precision that half the gas will be in the left chamber, half in the right. Other situations are just so unlikely you'd have to wait many, many ages of the universe before you would see them. So the macrostate with the most microstates, that is the macrostate that is the most disordered, is the most likely and is thus the one we will observe. That's a nice understanding, but can we make this observation perhaps more quantitative and more useful for thermal physics problems? To quantify this, we introduce the entropy, for which we use the letter S, capital S. The entropy S of a system in a macroscopic state that can be realized by W microscopic state is defined as the Boltzmann constant times the logarithm of W. The Boltzmann constant is named after Ludwig Boltzmann, on whose grave this equation is actually engraved. Boltzmann didn't invent entropy, that was Clausius a bit before him, but Boltzmann came up with this equation. Although technically not in that form, that one is due to Max Planck after Boltzmann's death, but nonetheless, the statistical interpretation of the entropy that Boltzmann came up with, that was his real main achievement. It was very controversial in its time. In fact, even atoms were controversial at the time. But I digress. Let's go back to the entropy. It is the log of W, the number of microstates that can realize a given macroscopic state. So clearly it depends on the macroscopic state and on the macroscopic state only. For macroscopic systems, this means the entropy solely depends on macroscopic state variables, such as the pressure, the temperature, the volume, etc. And importantly, it does not depend on the path taken to go to that state. So the entropy, very much like the internal energy, is a state function. It describes how many microscopic ways there are to make up a macroscopic state, and thus it measures the disorder of the system. Calculating W and thus S directly from microscopic consideration is very difficult and is the object of statistical physics, which you will see in coming years, in particular in third-year physics. Sometimes, however, changes in W can be calculated easily, as we'll see on Monday. We'll also see how to calculate entropy changes from a macroscopic perspective. Until then, cheerio.